Stuart, good catch on that definition. Yeah, but I'm not gonna bring it up just because I don't want to confuse people. I just let it sit as a flashcard, but you're right, that is the definition of the tangent plane.
Okay, yeah, that's fine.
Good catch. Just need you to be a math major. Just need you to be a math major. Okay, stand up, stand up, stand up. Get your videos on, get your videos on. I want to see your lovely faces. I want to see your lovely faces. Stretch, stretch. Oh, let's sit back down, let's sit back down. I'm just going to call on people that don't have their videos on. I'm going to have to make you guys answer all your questions. Lizzie, that ocean's making me really, really sad right now. I'm looking at that beach picture. Okay. Let's go back to high school. Let's start by going back to high school. What I want you to do is draw an XY plane. And draw a parabola. Like Dr. Warren, I'm liking Calc 3 today. I'm liking Calc 3 today, where we're going. Okay, so I ask you to do what? I ask you to do what? XY plane, and then I ask you to draw a parabola. And I'm willing to bet almost Pavlovian-like that 95% of the people in this room drew y equals x squared. I'm almost certain everybody drew y equals x squared. But are there a lot more parabolas? Are there a lot more parabolas than y equals x squared? Does anybody remember the general form for a parabola in the xy plane? It'll bring back nightmares. No, that's not it. Ax squared. Now, can you help me? Can you help me? Plus, oh crap, there's more. Plus b x plus c. How many of you remember that? Ax squared plus bx plus c. How much high school was built around? High school math was built around ax squared plus bx plus c. Now it so happens if you drew your parabola here, if you do parabola here, then chances are this is 1, this is 0, that's 0, which gives you your classic y equals x squared. Now if this is positive, what does that tell you about your parabola? Just going back to high school. If that's positive, what does that tell you about the parabola? It's smiling, it's always going up. If it's negative, what does that tell you about the parabola? It's frowning. If it's 0, you ain't got a parabola, you got a line. So, you know, so either if it's negative, then the parabola is going down. If it's positive, the parabola is going up. And you guys are zoning as if I'm doing this for fun, and this isn't going to be crucial later on when it gets so much harder. Okay, so now I want you to draw a parabola that's going down and crosses the x-axis in 2 locations. Okay, crosses the x-axis in 2 locations. So now you might not remember, but a parabola can move anywhere in 2-dimensional space. So I'm going to draw there. Where are the roots? Where does it cross the x-axis? Where does it cross the x-axis? You're like, Dr. Warren, there and there. Part of the time the parabola is positive, part of the time the parabola is negative. Most of the time the parabola is negative. Most of the time the parabola is negative. But part of the time it's positive, part of the time it's negative. So A would have to be what sign? We know A would have to be what sign? Negative. I know in this case, the A would have to be less than 0. If I wanted to find out when the parabola was positive, what part of the domain is the parabola positive on, and which part of the domain is the parabola negative on? Are sign charts important in calculus? Are sign charts important in calculus? Increase or decrease, concave up, concave down. Would it be nice to know those 2 values? Would it be nice to know those 2 values? So let's go back to high school. Does anybody remember in general how to find the roots of a general quadratic.
Turn y to 0.
You'd set y equal to 0. Okay, so then if we did that, we would have ax squared plus bx plus c equals 0. Now make your high school teachers so proud of you. Some of you guys were freshmen some of you guys were in high school last year. Not many of you, nobody in this room. Some of you were in high school last year. Does anybody remember what x has to be equal to? Oh, your teachers are crying. They don't know why they're crying. They're weeping right now at their seats. I'm going to write down one thing and the rest of it will follow. Negative b plus or minus. Now, what do you have after that? The square root of b squared minus 4ac all over 2a. And you were like so hopeful that you would never have to use the formula. You did it once or twice, you're like, this sucks. You know, I've got to have a calculator. I got to remember the plus or the minus. Okay? So we're thinking about it. This would give me the locations. This would give me the locations of my only two roots of this parabola. Does this make sense? Does this make sense? And so if I wanted to create a sign chart, then all I have to do is test one point here. Since these are the only zeros, then I would know if it's positive or it's negative. You know exactly when it's positive or negative. It's even easier. You can just look at A. You can just look at A. If A is in fact negative, then you know in between them it's positive, and beyond them they're negative. Does this make sense? This guy inside the square root was given a special name. Do you remember the name it was given? Make your high school teachers proud. There's 30 of you. Can anybody give me the name of that?
Discriminant.
Very good, Michael. He pulls it out. The discriminant. And what word's in the word discriminant? What's words in the word discriminant? Well, not specifically actually in the word, unless you spell like me. To discriminate. Doesn't that make sense? It's not a kind word. It's not a kind word anymore. But to discriminate. This thing discriminates between where you have a parabola that has two real roots or a parabola that has no real roots or a parabola that has just one real root. If b squared minus 4ac equals 0, then the plus or minus doesn't matter, and I just left with negative b over 2a. So this would be the discriminating case where I would have one real root. If b squared minus 4ac is negative, if b squared minus 4ac is negative, then I've got a negative under a square root. You're like, oh, that's not allowed in the domain. If you have a negative under a square root, then this is complex, which means then that there's no real roots, which would be which of my three drawings? Which would be which of my three drawings?
The third one.
The third one here. Now, if b squared minus 4ac is positive, then it discriminates and says you have two real roots, the plus or the minus, which you have this kind of scenario here. Or that kind of scenario there, if A is positive. Does this make sense? Is this bringing back memories? Okay, stand up, stretch. We're heading back on our death march. So you're going to want to have some water. Okay, sit back down. What were we talking about last time? What was the focus of last time's lecture? Monday's lecture. Local mins and maxes of a space sheet. Local mins and max. Do you think maxes and mins are important to bosses? If you have a multidimensional function, do you think local maxes and mins are important to bosses? Okay, draw yourself an XYZ. Mark 2, 3 down in the domain. At the point 2, 3, f of 2, 3, up on the space sheet, draw something that has a local max. Draw something that looks like it has a local max. So you should now have a space sheet that looks like it has a local max at 2, 3, f of 2, 3. Now, down in the domain, at the point 2, 3, draw a unit vector u, pointing away from 2, 3. Draw a line running through 2, 3 along that vector u. Nick, you have COVID?
No.
Okay, just. I saw all the spaces got taken for the COVID testing at U Park. Sorry, guys.
I got it at Mary Baldwin. And I saw some other people from my class.
I'm going to Mary Baldwin. I didn't know that was legal.
Well, they send like it in the JMU.
Oh, okay, good. Yeah, maybe I need to go to Mary Baldwin.
Every time is still open, so.
Oh, every time was still open. Okay. Mary Baldwin kids don't care about their parents, right? Okay. Now the hard part. Draw the space curve. Draw the space curve up on your space sheet corresponding to that line in the domain. And I'll give you a hint. It better go through your point 2, 3, f of 2, 3. It better go through your local max. How many people have a space curve? How many people have a space curve? Mark R of t beside that space curve. Mark R of t beside that space curve. Okay, find the 3 vector valued functions. Find the 3 vector valued functions that represent that R of t. That represents that space curve you just drew. Okay, now I'm gonna do what I made you guys do. What is the first thing I told you to do? X, Y, Z. What was the next thing I asked you guys to do? What was the next thing I asked you to do? Space sheet where I've got a local max. I'm not gonna be creative. I'm gonna draw like a bullet. With a flat curve like that. I guess I messed up. Maybe something like that. Give myself some reference down there. We're imagining this is the point. This would be f of 2, 3. This point would be, this point would be, this point would be, this point would be 2, 3, f of 2, 3. Okay, and then what I ask you to do? Then what did I ask you to do? Draw a unit vector, and again, I'm not gonna be so clever. There's you, okay? And then what did I ask you to do? Then what did I ask you to do? Draw a line running through this unit vector. And then what did I ask you to do? Then what did I ask you to do?
Draw a space curve on the space sheet.
Draw a space curve on the space sheet. So I'm imagining on this thing I've got there, this upside down part of an egg, that as I run through this, I'm going to be running behind, so you're not going to see that. Then I'm going to come up and go through this point right here, and then I'm going to come down along the front. I'm going to come down along the front of my egg. I'm going to come down along the front of my egg. How many people are with me? How many people are with me? How many people have got this? How many people are so far? Emily, are you there? Emily, is this making sense? Kind of? Okay, yeah. Welcome back. Raylan, is it making sense? Lizzie, is it making sense? Okay, then what did I ask you to do? Dr. Warren, I hate you. Mark it as RFT. So this space curve is RFT. It's a vector valued function. So I need three real valued functions. I need three real valued functions that represent that vector valued function. Well, the x and y are running along this. This line, right? The x and y are running along that line in the direction of u. So when I say line, you say a plus tu. Who's the a? Sorry, who has to be the a1? Who's the vector a?
2, 3.
2, 3, and my unit vectors, my direction vectors, u1, u2. Does that make sense? So what would be the first component? What would be the first component on the space curve? 2 plus tu1. That would run the x coordinate along that line. What would be the y function? 3 plus tu2. And now comes the hard part. How do I get up on the space curve? How do I get the z coordinate go up on the space curve? F evaluated at this and y evaluated at that. So I'd have f of, and then how many people are following? How many people are following so far? Okay, if this is actually going to be a local max, how must the tangent plane sit? It's got to sit dead flat. Does that make sense? It's got to sit up here dead flat. If it's not flat, if it's going like this, then some of the tangent vectors are pointing that way, and some of the tangent vectors are pointing that way. Which means in some of the directions u, I'd be going up, and in some of the other directions u's, I'd be going down, and you sure as hell aren't going to have a local max or local min. Does that make sense? You know, if the tangent vector is not, if the tangent plane is not dead flat, then some of the directions I'll be going up, and some of the directions I'll be going down. So this is our first requirement. For local maxes and local mins. If the gradient at 2, 3 does not equal the vector 0, if the gradient doesn't equal 0, then you know you don't have a local max or local min. And like Dr. Warren, why is that again? Well, does anybody remember the normal vector for the tangent plane? And I can see in your eyes, a lot of you are like, just make the semester end. I'm just hanging on until the end, Dr. Warren. I don't want to think anymore. I will give you a hint. Do not look at your notes. I will give you a hint. The last component in the z is 1. Does anybody remember what the first two components were?
Minus partial derivative of x with respect to xy.
That's the first one. Minus
negative partial derivative of x with respect to y.
Very good, Gordon. Very good. So guys, if the gradient's not zero, then this guy's not 0. And this guy's not 0. If they're both 0, then my normal vector is 0, 0, 1. If both of them are 0, it's 0, 0, 1. Who else has these? What vector is 0, 0, 1? I, J, or K? Which vector is 0, 0, 1? K, so I'd have my tangent, this would be the normal vector to the tangent plane, which means this would be like K, which means it's pointing straight up, which means then the tangent plane has to be dead flat. So does this make sense? Does this make sense? If the tangent plane's not dead flat, we don't have a local max or local min. Are you guys with me? So the first step in finding local maxes and local mins are finding where all the places where the gradient is. Let's try that again. I'm going to yell a little more. The first step in looking for local maxes and local mins are finding when the gradient is equal to 0. Finding when the gradient's equal to 0. Okay. Next, draw yourself an XYZ. And draw yourself a nice little curvy space curve, R of t. Not this one. Just draw yourself a nice little space curve, R of t. Okay, now for some value of t, we'll just mark it C. Put a position vector going from the origin to your space curve, and that'll just be the R of C. Now draw R prime of C. Draw the tangent vector. To your space curve at that point. The tangent vector points in the direction the curve is going. Is that the way, does that look right for you? Now comes the harder part. Draw something that could represent R double prime. For your space curve. Okay, and I'm gonna do the same thing I asked you guys to do. I just drew a space curve. Then I'm gonna ask you guys, I'm gonna pick a point on my space curve. Then I'm gonna draw this vector and mark it as, R of C. And then I ask you to do what? R prime of C. Would this be a good R prime of C? Hopefully everybody's like, Dr. Martin, what the hell? Right? Would this be a pretty decent R prime of C? Would that be a pretty decent R prime of C? Then I ask you to draw what? R double prime. R double prime points in the direction the curve is. Curving. So if I'm thinking about it, would it be on this side of the tangent vector or that side of the tangent vector? Would it be on this side of the tangent vector or that side of the tangent vector? And so, I'm looking at what I've got, and so roughly I'm guessing this might be like my R double prime of C. This would be like my R double prime of C. And like Dr. Warren, what was the reasoning of that again? Well, it goes back to the definition of R double prime of C. You say, Dr. Warren, I hate you. What's the definition of R double prime of C? Well, how do you find R double prime? Derivative of the derivative. Calculus is about limits, derivatives, and integrals. And we're going to have to get into integrals. We've got to get into integrals. We've been doing a lot of derivatives. Okay, everything's defined in terms of a limit. So R double prime of C would be defined in terms of a limit. It would be the limit as what? What's in your gray matter? It'd be the limit as what? This is when it's killing me not to have the cumulative final.
R prime of x minus R prime c. Or, I'm sorry, it defines the limit first.
You need a limit, yep, the limit as
T approaches 0.
t approaches c, we'll just go with c.
Right, okay.
Then we would have a,
R prime t minus R prime c.
all divided by
T minus c.
t minus c. Okay, and so if we're thinking, we're saying, okay, as t gets closer and closer to c, say that, then this limit gets closer and closer to that second derivative. Does that make sense? Does that make sense? Now all I'm interested in is the direction. What did I just say? This guy right here is just a what? T minus c. Well, it's going to 0, Dr. Warren. But geometrically, it's just a what in this game? It's a constant. Is it a vector or is it a scalar? It's a scalar. The direction of the vector is all in the numerator. It's r prime of t minus r prime of c. So let's move just slightly away. Let's move just slightly away and look at r of t. This is r of c. Now look at the numerator. It's r prime of t minus r prime of, but I already have an r prime of c. Let's draw the tangent vector. Let's draw the tangent vector for r prime of t. Now, could I move this vector anywhere I want in the room and have it still be the same vector? Some of you just are, you look like right now when I'm looking at the grid, just go to grid view, go to grid view, go to grid view, go to grid view, and look at those faces. Look at Robert's face. Robert, are you there? Robert. Okay, there we go. Look at those faces. Do those faces look eager to learn? Except Gordon's. Gordon's looks easier. Cosmos looks kind of, Zach, I'm not sure. Who's the guy in the middle? Oh, that's me. Okay. All right. So Emily, does that face look easier to learn? Emily's like, no. Rachel, a little dark there, Rachel. Can't see you, but I'm believing that's not eager to learn. Lizzie, that doesn't look eager to learn. Okay. Come back to where we were here. Let's see how we're doing, eager to learners. This is r prime of. This is r prime of t. Can I move this vector anywhere I want in the room and still have it be r prime of t? So I'm going to take this vector and I'm going to move it back to here. I'm going to take that vector and I'm going to move it back to there. This is still r prime of t. But look at the numerator. It's the vector r prime of t minus r prime of c, which would be this vector right here, which I'm going to move back to here. Do you see how that vector points in the direction the curve is curving? Do you see, just by working through the definition, this subtraction vector, this thing in the numerator, points in the direction the curve is curving? This is really important in today's argument. The second derivative points in the direction the curve is. The second derivative points in the direction the curve is curving. Stand up, stand up, stand up. Nick's first up. Cameron's like, just gonna write some stuff down.
Yeah.
You guys at home, Lizzie's finally up. Robert, you better be in the air. Luke, your butt better be not sitting. Ava, you better be up. Josh. Are you there, Josh? Josh.
Yeah, I'm here.
Are you up, Josh? Are you up?
Yes.
Okay, good. Okay, now sit back down. Okay, now comes the nightmare. Look at this space curve you just drew. Look at the space curve you just drew. Draw yourself a tangent plane. Draw yourself a tangent plane at the point 2, 3, f of 2, 3. Draw yourself a tangent plane at the point 2, 3, f of 2, 3. And I'll do the same thing. Now what I want you to do is I want you to tell me what value of t on your space curve, r of t, what value of t would put a position vector pointing to the top of your mountain? What value of t would put a position vector pointing to the top of your mountain? What value of t could I plug into here that would point to your location 2, 3, f of 2, 3? 0. If you plug a 0 in, let's just see. What do we get here?
2,
And what do I get there?
3,
And what do I get here?
f of 2, 3.
F of 2, 3. So this would be now what I want you to do on your graph, do the best of your ability to draw r prime of 0. For your space curve, it's got to lie in the tangent plane, so it's up there on that flat thing. Draw r prime of 0. Draw the tangent vector up on the tangent plane corresponding to your direction u. And I'm going to do the same thing. I'm up here at the top because t is 0. I'm up here at the top because t is 0. This thing's coming along my egg. This thing's riding along my egg like this. So I'm thinking my tangent vector is going to be up here in the tangent plane. Up here in the tangent plane. And I'm thinking that's my r prime of 0. I'm thinking that's like my r prime of 0. Does this make sense? Are you with me? Are you with me? Are you guys with me? In the grid, are you with me? Zach, is this making sense to you? Cosmo, is this making sense? Okay. Now, let's visually try to look at r double prime of 0. So you're looking at this space curve. Here's my tangent vector. On which side of the tangent plane do you think it's going to be on? On which side of the tangent plane do you think r double prime is going to be? Is it going to be on the upper part? Is it going to be up here? Or is it going to be down there? Below. If this is really a local max, then no matter where I point my direction u, I take my compass and point my direction u, won't that second derivative always point down if it's going to be a local max? And if it was going to be a local min, the curve's going to be going like this, which would mean I'd be pointing up. And that's the key. That's the key. You're like, Dr. Warren, what's the damn key? Ask me.
What's the name?
As long as the second derivative at 0 for any direction u is negative, sorry, not it being negative, as long as that z component is negative, as long as it's pointing down from the tangent plane, I know I've got myself a local max. If it's pointing up, I have myself a local min. Now here's the problem. We need that derivative. What do you mean, Dr. Warren? I need to analyze this derivative, which means you've got to take the, not Dr. Warren, you've got to take the derivative of this, and you're not done, you also need to take the derivative of that. So at your seats, take the derivative. Let's start off easy. Find r prime of t. You guys get busy. Find r prime of t. You've got your space curve r of t. Find r prime of t. And this will help you for Friday's quest. This will help you for Friday's quest. How many people think chain rule might be on Friday's quest? I mean, if you just wondered, how many people think chain rule might be on Friday's quest? Okay, for sake of time, I'm gonna help. How many people are pretty comfortable with taking the derivative of the first? How many people are like, I got you Dr. 1 for x prime of t. What's the derivative of this with respect to t? u1. The derivative of this is 0, this is a constant, this is t, so I just get a u1. How many people are with me? How many people are with me? How many people are with me? Okay, how about the second component function? What's the derivative of that? u2. Like Dr. 1, this ain't bad. No, it's bad. Okay. How about if I want to take the derivative of this? Is f pregnant with two functions? What rule do you have to use to take derivatives of pregnant functions? Chain rule. This is a multidimensional chain rule. So you guys help me out. It's going to be using your chain rule. It's going to be the partial derivative with respect to x. Now I'm going to get lazy. I'm not writing these down all the time. I'm not writing them down all the time. I'm getting lazy. I know it's 2 plus tu1 and 3 plus tu2. Am I done? Am I done? And please say no. Now I got to take the derivative of this with respect to t, and what do you do when you get that? What do you get when you do that? u1. Am I done? No. There's a big what in our chain rule? Plus, now with respect to y, again, I'm getting lazy. I'm not writing down the 2 plus tu1 and so on. Times y prime, but y prime would be u2. How many people are with me? How many people are with me so far? How many people are with me? Okay, but I don't want r prime. I don't want r prime. The answer is going to come from r double prime. So now, to the best of your ability, try to find the acceleration vector. Try to find r double prime. And you can use the lazy notation if you want. Oh, I will, Dr. Warren, I will. Okay, for sake of time, I did it for you. For sake of time, I did it for you. So I'm going to see how you guys did. The first one you're like is so nice. What's the derivative of u1 for a fixed vector? 0. Like Dr. Warren, we're off to a great start. What's the derivative of this? 0. Now this is what's disappointing. I come to take the derivative of this, but this is pregnant with 2 plus tu1 and 3 plus tu2. This is a function that's also pregnant. You've got to use what again? Chain rule. And so that's what I did. I used chain rule on that function. this U1 doesn't show up again until right there. That U1 is hanging right there. My U2 is way, way over here. My U2 is way, way over there. So let's use chain rule again. Well, it's going to be another derivative with respect to x evaluated at 2, t1, 2tu1, and so on, times u1, the derivative of the inside, plus the derivative of this guy with respect to y, evaluated at the inside, times the derivative of the second component, which is u2. How many people are following? How many people are following? And then I've got to take the derivative of this, but again, I've got to use chain rule. So it's going to be the derivative of this guy with respect to x, again, times the derivative of my, what's in there, which would give me my u1, and then finally my fyy, u2, and then times the u2, which is, this guy is all the way over there. It's a lot. I know it's a lot. Some people say it's impossible. They'll never understand this. And I say, no, it's not impossible. It's cumbersome. How many people are with me? How many people are with me? We've just used chain rule. We've just used chain rule twice. Now I want you to look at this R double prime for a moment. I know no matter what I said right then, nobody. This is when I can't, I mean, normally I just, okay, I'll do this. Can you guys still see me in the grid? Can you still see me in the grid? Okay, this just gives you something else to look at. And here it's much more impressive. But this is kind of fun, Superman. Okay. What are you doing, Dr. Warner? Awkward silence. I used to do it on dates too, okay? Just, somebody has to be special to be able to live with me. Dr. Warner, I believe that. Okay. I'm now getting down. This is the most focused you've been all day. I mean, I don't know what it is. I stand on the desk and sit quiet, and all of your eyes are zeroed in on me. Like, what's he going to do next? If I teach you zone, let's look at R double prime of t. Let's look at R double prime of t. The first component is 0. The second component is 0. What's the sign of the third component? That's what we want to know. This is a vector that always points straight up or straight down. This is 0. This is 0. This nasty thing here determines the entire sign of this thing. It either points straight up or it points straight down. If this thing is positive, from my double chain rule, the vector points up. If this thing is negative, the vector points down. If we could argue that this nasty thing at 2, 3, f of 2, 3 always points down, irregardless of what u is. If it always points down, I don't know why I feel like that's teaching. If it always points down, then that means the curve is always curving down, which means I'd have a local maximum. If I could argue that it always pointed up, irregardless of which direction ui went, then I'd have a local minimum. Does this make sense? What value of t puts it up here? What value of t actually puts that R double prime at the point 2, 3, f of 2, 3? Well, what value of t got us up here with the position vector? 0. What value got the velocity vector pointing in this direction? 0. So let's evaluate our R double prime. Let's evaluate our R double prime at 0. So go ahead, evaluate your R double prime at 0. You're like, that's when there's a lot of big blanks in there. Well, you should still be able to figure it out. If you get the first two components wrong, I'm just going to vomit on the iPad. Okay, wherever I have a blank, I'm going to put a what, guys? Wherever I have a blank, you're going to put a what? 2, 3. Wherever you have a blank, when t is 0, you're going to have a 2, 3. Now, for time, guys, I'm going to distribute my u1s. I'm going to distribute my u1, and I'm also going to distribute my u2. And so if I do this, I would have a fxx at 2, 3 times u1 squared plus an fxy at 2, 3 times a u2 u1. I'm going to this one. I would have a fyx of 2, 3 times a u1, u2, and then my last term in this component would be a fyy of 2, 3 times a u2 squared. How many people got that? How many people got that? How many people? Anybody get that in the grid? Anybody at all get that in the grid? Just Cosmo, okay, Gordon. Zach, did you get that? Zach, does this make sense? Rachel, did you get this? Kind of. Okay, what does Claret's theorem tell us? I hate you, Dr. Warren. What does Claret's theorem tell us?
That f of xy equals f of yx if the partial derivatives are continuous.
Very good, Gordon. If the partial derivatives are continuous, then fxy is the same thing as fyx. Now look at this. Here I've got a u1, u2. Here I've got a u1, u2. And you guys can't see at home. Here you've got a u1, u2. But here you've got a u2, u1. Aren't these the exact same thing? Aren't these the exact same thing? Okay, so how many of these would you have? How many of these would you have? 2. So now, unfortunately, I've got to erase stuff. So I'm going to go up here. So forget about the vector. Let's just look at the last component. It'd be fxx at 2, 3 times u1 squared plus 2 fxy at 2, 3, since they're the same, times u1 times u1 u2. And then what's the last term? What's the last term in that? Cleaned up here a little bit. I have a, what's the last term? fyy at 2, 3 times u2 squared. Okay, let's take the helicopter out of the woods. First thing I ask you to do is draw an XYZ. True or false? True or false? Mark a 2, 3. Draw a space sheet with a local max at 2, 3, f of 2, 3. Draw a unit vector u. Draw the line, draw the corresponding space curve, figure out what the space curve was, which I've now erased. Then we decided that the tangent plane would have to be flat, which meant the gradient had to be 0, And then we decided that as long as the second derivative always pointed down, we would have a local maximum, irregardless of the direction u we spin this. And that's the hard part. How many direction u's are there? How many direction u's are there? How many are there? Infinitely many. And you're like, Dr. Warren, you're totally screwed. And so it seems. U1 and U2 could be a lot of different things. I want to argue it's always got to be negative. How are you going to do that, Dr. Warren? Say that.
How are you gonna do this, Dr. Warren?
With more enthusiasm.
How are you gonna do that, Dr. Warren?
Because it's kind of miraculous that I can. You guys, I mean, it's like for some of you, I feel like, let's just do this. Come on, do this. If you're not feeling anything, Zach. If you're not feeling anything, man, then we've got issues. Ava, are you getting any pulse? Ava, I'm getting concerned. Okay, good, there's the pulse. You're not gonna like what I'm gonna do next. But I'm trying to do the impossible. What I'm gonna do is I'm gonna factor one of these guys, either this guy or that guy. Nick, either this guy or that guy out of all three terms. You pick, it doesn't really matter. Do you want me to pull the u2 squared out, or do you want me to pull the u1 squared out? You guys pick. Do you want me to pull the u2 squared out or the u1 squared out? Okay, I'm going to pull the u2 squared out, and I'm going to pull it all the way to the front. I'm going to pull that u2 squared out of all three of those terms. You're like, Dr. Warren, you can't do that. Oh, yes, I can. If I pull a u2 squared out of this term, it's the only one you understand. If I pull a u2 squared out of this term, what do I have? A 1, so I would just have a fyy. So let's put that in there. It's the only term we really understand. Now, let's screw the middle term for a second. Let's just go to the first term. If I pull a u2 squared out, you're like, Dr. Warren, man, you ain't got a u2 squared. What do you mean pull it out? If I pull a u2 squared out, I would have an fxx of 2, 3, and then I'd have a u1 squared divided by a u1 squared divided by a u2 squared. I'm not going to write it like you think I'm going to write it. I'm going to write it like this. Now I'm going to ask, is that the same thing? Is that the same thing? How many people are following? How many people are following? Okay, now let's look at the middle term. I've got the 2 in the partial derivative there. Now I'm going to pull a u2 squared out. This one's the most complicated. I've got myself a u2 here. That's going to go away. That u2 is going to go out there. But I'm pulling a u2 squared out. So what would be left here? What would be left there if I pulled a u2 squared out?
U1 over U2.
u1 over u2. Dr. Warren, how the hell are you going to argue this is negative? So ask that again. How can you possibly argue when this is going to be negative? Okay, I want you to squint. So squint up here. Squint. Some of you in the grid aren't squinting. If I stare at this, if I stare at what's inside here, I can see a parabola. You're like, no, Dr. Warren, you don't see a parabola. No, I really kind of see a parabola. And you're like, no, Dr. Warren, you don't see a parabola. If I look at it kind of here, this is just a number, A. I kind of have this guy out here, u2 squared. If I call u1 over u2 capital X, then I would have an A capital X squared. And if I call this guy like B, then I would have a B times X plus C. I've got a parabola. if I want my parabola to always be negative, go back and draw yourself a parabola in the xy plane that's always negative. Draw a parabola that's always negative. First of all, which way does it have to flip? Which way does it have to flip? It's always going to be negative. Down. So what would the sign of capital A have to be? Negative. So if it's going to be negative, my first test is I need fxx at 2, 3 to be negative. I need that to be less than 0. If I had pulled the u1 squared out instead of the u2 squared out, the only difference would be this would be my a. This would be my a. And so I'm just helping us as we start running out of time. We could also need that to be negative, but don't worry about that. I'll fix that later. If a parabola is always negative, how many roots does it have? If a parabola is always negative, how many roots does it have? 0. In which of my 3 cases am I, if I'm asking about who's discriminating? In which of my 3 cases is it, if I'm talking about this thing discriminating? Would it be equal to 0? Would it be less than 0, or would it be greater than 0? Less than 0. That was a good verb. Coming from the grid. I don't know who burped their grid. I like that. That's my daughters do that. They burp. And I'm just like, who came up with that idea? Sugar and spice and everything nice. There's nothing about that little girls are made of. Nothing. Nothing about that. My daughters, yeah, okay. Sugar and spice. Okay, so you guys tell me out. Who's the B? Who's the B? Who's the B? Who's the B in my parabola? Who's the B?
fxy.
2fxy. 2fxy. So I would have a 2fxy at 2, 3 squared minus 4 times, who's A? Who's A? fxx at 2, 3. And who's the C in this case? Who's the C in this case? fyy at 2, 3. And I would always want this to be negative. I would always want this to be negative. Now what is 2 squared? What is 2 squared? What is 2 squared? I know that's hard. What is 2 squared? What is 2 squared? 4. Do I have a 4 here already? If I square this, do I get a 4? Do I get a 4? Could I pull the 4 out? Could I pull the 4 out? Is 4 always positive? Is 4 always positive? So I don't even really need to worry about the 4. If I factor it out, this is what I need. I need either, if it's a local max, both will be negative. You don't have to worry about it. If it's a local max, both of these guys will be negative. But this is what you really need. You need that squared to be negative. If this is negative, if the discriminant is negative, say that, and these are negative, then I know that in every direction I go, that last component in R double prime will always be negative, which means I'll have a local maximum. Now suppose this is positive. This is positive and this is negative. Then I have a parabola that never crosses the x-axis, but since A is positive, it's opening up. Then every direction I go, my R double prime points up, which would mean I'd have a local minimum. Now notice, guys, these don't depend on you. They're completely independent on you. That's what makes this work. It's really clever, whoever came up with it, and it wasn't Dr. Warren. This is really clever. How many people are getting comfortable taking partial derivatives? How many people are getting pretty comfortable taking partial derivatives? I'm over time. Okay, on Friday, before you take your quest, I'm gonna work one example showing you guys how to do this, and then I'll give you your quest. I'll work one actual example showing you guys how to do this.
Doctor, when we go to 11.
Oh, great! I can show you guys an example. Never mind, I lied. Doggone it, how many, I mean, you'd think like I'd eventually learn, except like anybody who taught me realized that was not gonna happen. Did I tell you they wanted to hold me back did I tell you they wanted to hold me back in second grade? Did I tell you that? They wanted to hold me back in second grade and my mom wouldn't let them because my sister was 1 year younger than me, who was a genius, and they thought it would be too defeating. And you'd think that would be enough for me to get my act together, but this happened in 3rd grade, 4th grade, and 5th grade. All 4 of those years, they wanted to hold me back, and my mom wouldn't let it happen. My mom wouldn't let it happen. I'm not sure it was a good thing. As I look back, I'm not sure it was a good thing. I was probably a little young. My birthday was in June, and so I never quite felt. And like when I was in 7th grade and they made us dress out for gym class, I always felt like I was in a locker room of men, and I was the only boy in the locker room. I was just like, you gotta be kidding me, you know? Some guy's 6'5" and shaving, it seemed, in 7th grade. And some other guys like my height. I grew 7 inches. 7 inches in 9th grade alone. 7 inches. I went from being 5'6" to 6'2", and now I'm 6'1". So look at what you got to look forward to. Every time I look at myself in the videos, I'm like, oh my gosh, I'm slouching. I'm gonna look at that. Oh my gosh, this is horrible. Oh my gosh, I need a haircut. Oh my gosh, I'm going bald. Yeah, it's just horrible looking at videos of yourself. Okay. Let's talk about a step-by-step method for finding local maxes and local mins. Are you willing to be with me? Are you willing? What did I just say? Step-by-step method after a little Dr. Warren commercial. The first thing you know, if the gradient's not 0, if the gradient's not 0, your tangent plane's not flat, you don't have a local max or local min. Does this make sense? So step 1, write this down. Find all the places x, y where the gradient is 0. And I'll do the same thing. So those are your critical points. Those are the critical points. Those are the only places where you could possibly have a local max or local min. Now you guys, let's see if you remember for the quest on Friday, what does the gradient actually mean? What vector is the gradient vector? Oh great, we're screwed. Okay, what is the gradient vector?
Partial derivative of f with respect to x, y, partial derivative of y, y.
And I need this to be equal to 0, 0. So I need all of the xy's that make this 0, but I'm not done. It also needs to make the second function 0. How many people are getting comfortable taking partial derivatives now? I mean, if you haven't done your homework, then you're screwed. But I mean, how many people are getting more comfortable taking partial derivatives? Okay, next, what you need to do is to get the second partials. They show up in the discriminant. What other partial do I need? What other second partial do I need? Anyone? X, Y. And then, what other one do I need? F, Y, Y. Now, as long as I'm kind, it's not so hard to find these. If you can find this, you can find that. If you can find this, you can find that. If you can find this, you can find both of those. If you know how to take partial derivatives, this isn't so bad. The next thing you've got to do is gather up all of your critical points in the domain. You find all the values x and y. What did I just say? That make this 0 and this 0. So let's just suppose one of the points down there in the domain is A1, B1. Suppose that's a critical point. So when you plug A1 and B1 into this, you better get a what? You better be getting a what? If you plug an A1 and a B1 in here, and it's a critical point, this thing better be 0, and this thing better be 0, or it's not a critical point. And let's suppose that there's 3 critical points. Are there more, Dr. Warren? Yeah, there's some problems that have 6. Would you put that on the quest? No. Will this be on the quest on Friday? The answer is no. The next thing you want to do is set up your discriminant. And our discriminant is fxy squared. So next thing you want to do is plug your A1 and B1 into here, here, and here. What did I just say? What did I just say? Into this second partial, and this second partial. They're now numbers. They're now numbers. Then you check this number. This squared minus this squared times that squared. If this is positive, if this ends up being positive, then that means the parabola isn't always positive and the parabola isn't always negative. That means in some directions you're going up, in some directions that's going up, in other directions it's going down, which means sometimes it's curving up and sometimes it's curving down. You got a saddle point. So if this is positive, you've got a saddle point at A1, B1. And it's not a local max and it's not a local max and it's not a local min. I'm getting lazy. If it's negative, if it's negative, you know you have if it's negative, you know you have a local max or a local min. You just got to figure out which one is it. If it's negative, you know you have a local max or a local min. If either one of these, now notice you've already calculated these. These have already been, what did I just say? You've already, if this is negative, then this will be negative. If this is negative, then this will be negative. If this is less than 0 or this is less than 0, the parabola is always going down, never has any roots. So then I know I have a local, then I know I have a local max.
Max.
If they're both positive, then I know we're always going up, which would mean I'd have a local min. And that's the way this works. It's in the book. This is essentially your second derivative test. This is essentially your second derivative test for multidimensional functions. Okay, one example, and then I'm going to let you go. So I'm going to pick one that's easy for me to do. This is 14.7. Let's look at problem number 11. The hardest part is finding the critical points. If you can find the critical points, you're in good shape. So here's my space sheet. F of xy, I'll read it off. F of xy is equal to x cubed minus 3x plus 3x y squared. So there's my space sheet. There's my space sheet. I'm looking for local maxes and local mins. What's step one? I erased it. What's step one? Find your partial with respect to x and your partial. So you guys do that. Find fx and fy. And I'm hoping on the quest you'd be done. I'm hoping on the quest you'd be done. If you're coming up here you're treating who as a constant. Here you're treating who as a constant. Y. So what would the derivative of that be with respect to x? What would the partial derivative of this with respect to x be? How many people are following? How many people are following? What would the partial derivative of this last term be?
3y squared.
Plus 3y squared. And I'm looking for all the x, y's that'll make this 0. You're like, this sucks, Dr. Warren. And we're not done. Here's my second component. Here's my second component. Find the partial derivative with respect to y. And this is where they make it a little bit better for us. Here I would get a 0. Here I would get a 0. And here I would get a 3, 6xy. How many people are following so far? Most of the time, this is not the part that kids get screwed up with. How many people are following? If it's a critical point, if it's an A1, B1, and it's a critical point, it has to make this
0
and this 0. Which one's going to be simplest in the beginning to analyze for it being 0? You know, like, how about this one? So let's set that equal to 0. If I do that, then I would have 6x times y has to be equal to 0. How many people are following? How many people are following? Can 6 ever be 0? Then that means either x is 0 or y is 0. So that's my first condition. I know the second partial being 0 requires that. Now draw yourself an xyz. Draw yourself an xyz. I'm down here in my domain. And I know my critical points have to either occur on the line x equals 0, which is this line right here, or on the line y equals 0. So I know my critical points are somewhere on these coordinate axes. They're somewhere on there. Like, where are they, Dr. Warren? Well, let's use our second partial. Let's look at the case x is 0. But if x is 0, and I want this to be 0, when you plug a 0 in, what do you guys get there? When you plug a 0 in, what do you get? When you plug a 0 in for x into this first partial, what do you get? Minus 3 plus 3 y squared. And I need this to be what? 0. Which would imply that y squared, 3 times y squared minus 1 is 0, which would mean y is either plus or minus 1. is this get us back from high school? So you have two critical points. What are your two critical points? From this, you have two critical points. Can you figure this out? This is what I need you to do. We're out of time. What are your two critical points from this? X was 0. And y ended up needing to be either
Plus or
One.
minus 1.
plus or minus 1. So there are two critical points. You know that this is a critical point when y is plus 1, y is minus 1. That's just the case when x is 0. I have the other case when y is 0. Now when you plug a 0 in for y, what do you get? When you plug a 0 in for y, what do you get? 3x squared minus 3 equals 0. Which is the same thing. Which would mean I would have, which is going to mean that x is equal to plus or minus 1. So what critical points do you get out of that? What critical points do you get out of that? 1, 0, and negative 1, 0. They're like, Dr. Warren, they're the same. Hell no, they're not. This is on the x-axis, this is on the y-axis. Now what do, Dr. Warren? Well, you gotta take the second partials and find the discriminant for each one of those. We'll pick up with this on Wednesday. On Friday. I'll do a little bit more with this, then I'll give you a request. Sorry guys, I didn't get as far as I wanted. Thanks for putting up with this. Is a tough lecture, I get it. Thanks for coming in playing, Sean.
Is today's lecture gonna be on?
No, nothing today, and most of the last time's not gonna be on.
Okay.
Anything with maxes and meds aren't gonna be on there, anything with maxes. I mean, the definitions of local maxes and meds.
They
are
are.
on there.
Okay. That's it?
That's it, yeah,
Oh.
but that's in those flashcards I sent out. Thanks, Stuart, thank you.
Will there be any sort of proofs on the test after
Oh
one?
yeah, there could definitely be some arguments, I doubt there'd be proofs, but there could definitely be
Okay.
arguments. We didn't cover everything in every section, but Nick, I think it's 14.3, 14.4, 14.5, and 14.6. But just like, it's directional derivatives, gradients,
If we see anything crazy, we'll just.
yeah, partial derivatives. I mean, the nice thing is it builds on itself, so if you know how to do partial derivatives, it's gonna help you to do the rest of them. Thanks, guys, thank you. I just can't believe I'm not gonna see faces after, I may have to cheat.